So guys, now look at a rolling motion. If you have, that's animated rotation. So now you look at this animation, you have the object translating because the center of mass is moving, and it's rotating because around the center of mass. So this is where we say that the kinetic energy is partially rotational kinetic energy and partially translational kinetic energy. Look at that example here. If we have a rolling system, an object that rolls, yes.
The number of the two objects will be the same because the masses will not change. The distance between them will not change. So the center of mass
Center of mass relative to what?
to the two objects.
Oh, of course it will not change, but that's what we do. We measure the motion relative to an inertial reference frame. We measure anything relative to a frame that's not accelerating
To the ground.
to the ground. So if I say this is the object, and if it now where is the center of mass? Okay. Where is the center of mass? Oh no, here is not a quantitative answer.
5G.
So where is the center of mass?
5ITZ.
I say it again.
There, 5I.
5I
TZ.
and 2J. So I is saying it's 5 meters, which is not really 5, but 5 meters from the origin along the x-axis and 2 meters from the origin along the y-axis. So your center of mass is located at 5 and 2. That's what Ali says. Now, yeah, of course. When I say the center of mass, we mean the location of the center of mass. When we say center of mass, we mean the position of the center of mass. Right? This is the definition of the center of mass. When I say center of mass, what does the center of mass mean? No, position. 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 It's a point in space. This is the meaning of center of mass. It's a point in space. And when we talk about a point in space, then we're talking about the position of that point, the location, as you said, of that point. So I said the location of that point, or the position of that point, it's 5 and 2. Right? Now, what is the position of the center of mass? Where is the center of mass? 8 and 2. Did the center of mass change? When I say center of mass, by default, it's a position. It's the location. There's nothing called, okay guys, there's nothing called center of mass. It's the position of the center of mass. So for simplicity, but instead of saying the position of the center of mass, we say the center of mass. But it's the meaning of it, it's actually the position of the center of mass. So did the center of mass change? Yes? Now it's at 8 and 2. So that means that we have a translational motion. And if it rotates as well, then we have a rotational motion as well. Heidi. Yes. Yes. Yeah, it's somewhere in here.
Yes. So it's not 8 and 2 or 5 or 2.
Oh, yeah. We measure it relative to an inertial reference frame. So a frame that's not accelerating, which is the ground. But if I do this, Ahmed, catch. Okay? So now, how can you measure the motion of the center of mass? Actually, if you sit on that marker, at one end of the marker is not moving. In your car, if you actually put the shades on and you cannot see outside, whatever the speed of the car is, you're not moving. You're not moving relative to your car. Right? When you sit on your seat in your car, are you moving relative to your car? So if you sit on that marker, one end sits on that marker, is the marker moving? No. No. If you sit on that marker,
The marker is not moving. I relative to the marker, I'm moving.
No?
I'm not moving.
You're not moving relative to the marker is not moving relative to you. Right?
And what the next direction is.
Right?
What the next direction is.
Moving together, yeah, parallel to each other.
Yeah. You're not moving. If you're moving relative to the marker, then your position relative to one end has to change, and it does not change. So you're not moving relative to the marker, and the marker is not moving relative to you. But relative to someone outside, us, sitting in class, watching this, yes, the marker is moving, and if you're sitting in here, and you're moving too. So when I say the position of the center of mass, when I say the center of mass, I mean the position of the center of mass. And when I say, did the position of the center of mass change? We have to measure it relative to a frame that's not accelerating. Ground, in that case, Earth. So in that case, the center of mass is changing.
So that's why when I calculate center of mass, I have to make X and Y.
That's why when I do this, I ask you guys where is the center of mass. Before we do this, we have to choose a coordinate system. Okay? And for simplicity, this is what we did. As we said in the very first lecture, we're free to choose our coordinate system wherever we want. So I choose it in here. I'm just simplifying the calculation of the center of mass. When I say the position of the center of mass, it's this relative to the origin. Okay? And when I do this, now guys, this is the origin. Where is the center of mass? Here. Of course, I do not move the origin. When I move the marker, do we move the origin with it? The origin stays the same. Did the center of mass change? Here you go. Okay? So the center of mass has changed now. I do not move the origin. So when I choose that one end of the marker to be my origin at the beginning, and then when I do this, I do not do this. I do not move my origin with it. I just move the marker. Keep the origin the same. Otherwise, I'm facing two different situations.
So what's the moment of inertia have to do with the center of mass?
Oh, okay. That's good. Now, if I ask you, what is the mode of inertia of that thingy?
Has to rotate.
Oh, no. Without rotating, it has a center of mass. Sorry, it has a mode of inertia. But when I ask you, what is the mode of inertia of that? This is not a complete question in here. I'm missing something. I'm missing the pivot where is the rotation is around. So if I ask you, well, what is the moment of inertia around the center of mass? 1/3 ml squared. What is the moment of inertia around one end? It's going to be a different value. What is the moment of inertia around that port? It's going to be a total different value.
But the center of mass is calculated according to the...
Yes. Okay. Taha, would you please sit in here? So now, let's look at this. We have an object that's going to roll, that's a sphere. That's a sphere. And that object is going to roll down in here, and we need to find the velocity at the end. So it starts from initial velocity equal to 0. Of course, omega will equal to 0 at that case. Kinetic energy will equal to 0 as well. At the end, the velocity, it will go down a height h. The velocity will equal to omega r. This is what we know, the relation between a linear velocity and angular velocity. The kinetic energy in that case, this is from chapter 8, change in the kinetic energy will equal to negative the change of the potential energy, should equal to mgh. So in that case, what will be the kinetic energy? What will be the kinetic energy? Should I say the kinetic energy is only half mv squared? No, because also we have a rotation.
But it could be mgh.
Oh, that's the potential energy. So the potential energy is mgh. When it goes down here, when it rolls down here, at the end it will have a velocity. In order to calculate that velocity, I have to find out what will be the kinetic energy. So I have to equate the kinetic energy to the potential energy. So I have to say that the change in the kinetic energy equals to mgh. And the change in the kinetic energy in that case is not half mv squared. It's half mv squared plus half I omega squared. Let me give you an example for that. What is that chair? Broken chair. There was a broken chair. What is it? Okay, anyway. Two different motions. Look at those motions. Vanessa, if you can stand up for a minute, just to see. So look at this. If that moves down like that, what is the kinetic energy? Half mv squared. That's it. There is no rotation. It's half mv squared. Right? If I do this, the center of mass has moved, then we have half mv squared and half I omega squared. So now I have to include that part in the kinetic energy. I cannot just simply say, as we used to say in chapter 7 and 8, that the kinetic energy is half mv squared. Not anymore. Now we have rotation, we have to add to it the rotational kinetic energy. Okay, guys?
So the MGH is just equated to
The mgh equal to all of that. Then look at this. I'm going to write that equation on the board. mgh will equal to half I omega squared plus half m v squared. Look at that equation. How many unknowns do we have? Look at that equation. We know the mass, we know the height. Guys, we know the mass, we know the height, we know, of course, g. How many unknowns do we have? We know the I. We can calculate the I. If I give you this is a sphere, then we can calculate the I. We have, of course. Yeah, it's given I. I gave you I. Can we solve that equation? No.
We can do it
No.
if we did this.
Yes, true. We cannot solve that equation because it has two unknowns, v and omega, unless we relate v to omega. Now we have two equations in two unknowns that can be solved. And most important is that equation that relates the linear motion to the rotational motion, v equal to omega r. Now we can solve that equation. Okay, guys? Ali? Okay? Okay. That's assuming that there is no slipping. Okay, I'm gonna get into business. Skip that part. Okay. If something that rotates, if I rotate that object like this, what is the direction of the rotation? Right? It rotates around this, and I have to choose a direction of the rotation. I have to choose a coordinate to say this rotates in the z direction, it rotates in the I direction. So we use what we call the right-hand rule. The right-hand rule is you bend your hands in the direction of the rotation, your thumb will point into a direction, this will be the direction, we'll call that the direction of the rotation. Okay, so that door. That door. When I rotate it that way, open it. So what is the direction of the rotation? Right hand rule, it rotates in that direction, it actually rotates in that direction. This will be my direction of the rotation. So negative y in that case. Oh, actually this is a rule that we have to come up with. That's something that all scientists that agreed on. We need to specify a direction for the rotation. This is in magnetism later on. When you come and take physics 112, I will tell you more about this. Okay, so we need to find a direction for the rotation. We need to when we want to describe something, we need coordinates. Chief. We need coordinates in order to describe directions, right? So if that door rotates, scientists said we're going to use what we call the right-hand rule. You're going to bend your fingers in the direction of the rotation. Your thumb will point into a direction perpendicular to that. We'll say that this is the direction of the rotation. So now let's assume that that lamp here, I'm going to rotate it that direction. So what will be the direction of the rotation? Up. If I rotate it that direction. So now we can find a direction for any rotation. And we will need that in a minute when we go and calculate the torque that we talked about last time. Well, actually, we introduced last time. So scientists said that if you have a counterclockwise rotation, we would say that this is the positive z direction. So if the object rotates counterclockwise, then this is the positive z direction. If the object rotates clockwise, then this is into the page, this is negative z direction. So just this is a convenience. This is exactly like choosing coordinates at the very first lecture. Not important. Okay. Look at that example here. We have a ball that rolls across the floor. This is the ball that rolls across the floor. A pole that rolls across the floor, and it goes up that ramp. In what direction does the angular acceleration vector point? Angular acceleration. In what direction is the rotation? In what direction is the rotation? Not the forget the angular acceleration for now. So it rotates that, so it's into the page. That's the direction of the rotation, correct? Into the page. Now we need to talk about the angular acceleration when the ball is rolling up the ramp. Yes.
We have to know
It's alpha, yes. Omega is the velocity, angular velocity. Direction of the rotation, this is exactly what I'm asking you. B, which is into the page, is it? So, are you saying that the direction of the motion is going to be the direction of the acceleration?
No, the angular acceleration is the change of omega, which is the change of theta.
Mm-hmm.
So it's not into the page.
Okay, guys, let me tell you something. Let's go back to chapter 2. Chapter 2. Translational motion. If I move in that direction, what is the direction of my motion? If I speed up means I'm increasing my speed as I go on. If I can speed up when I go to that direction, what is the direction of the acceleration? So if I assume that I'm already starting with high speed, then I will slow down. So I started with high speed, then I will slow down. In the part that I'm slowing down, what is the direction of my acceleration? The direction of the acceleration has nothing to do with the direction of the motion.
Why?
Now I'm moving in that direction, and my acceleration in the opposite direction. Yeah. So now you have to take that into consideration when we look at that problem again. When it goes up, is it slowing down or is it speeding up? Slowing down. Because actually it's going up against the gravity, so it's slowing down. So the acceleration, if the rotation, if it rotates in that direction, then the acceleration is going to be out of the page.
In the case of deceleration, right?
Yes. Is this accelerating or is it decelerating?
It means whatever
Taha.
the acceleration or the deceleration will be in the opposite direction if the distance is slowing down.
Yeah, and then in that specific problem, what will be the direction of the acceleration is down the ramp? Out of the page. When we talk about angular acceleration, but when we talk about acceleration, linear acceleration, then you're right, it's down the ramp. Okay? So that's alpha, and so you're right, backspace. Here you go, out of the page as we solved it. Now, look at this. Assume that I have an object that has a mass m, and it rotates in that circle, and it rotates with an acceleration, angular acceleration equal to alpha. The distance between the object and the center of that circle is r. The acceleration, linear acceleration, is a, and we'll have a force F acting on. So in order to make that rotate, I pull it always with the force F. That's the force F. That will have two components. One of them is tangential component, that's F theta, and one of them is radial component, I will call it Fr. Now let's look at this situation now. I'm very interested in finding out the force acting on that object. So I'm going to say that what makes that object rotate, is that A theta that keeps on rotating that object. So A theta, by definition, that's the alpha times r, linear acceleration equal angular acceleration times r. So the force F theta is going to be the mass times the A theta. It's the mass times alpha times r. Multiply that whole equation by r. Just multiply it by r. You get r times F theta, r times the force F, that component of the force, blue part of the force, will equal to m alpha times r squared. That's mr squared alpha. Remind me again, guys, if you have a point that rotates, if you have an object that rotates, what will be the moment of inertia of that point? Mr squared. So simply that mr squared is the moment of inertia. So again, that means that r times F theta equal to moment of inertia times alpha. R times F theta will equal to the moment of inertia times alpha. that R times F theta, I'm going to call it another physical quantity, that's a torque. So R times F theta, that's the torque. Torque equal to I alpha. Now we have another form of Newton's second law. And this form now is for rotational motion. We have agreed in chapter 5 that the sum of the forces will equal to mass times acceleration. The net force on any object will equal to its mass times its acceleration. That's if the object is moving, is having a translational motion. But if that object rotates, what makes that object rotate? Look, what makes it rotate? Forces. So you have to fix it at some place and you push it with a force, then it will rotate. So what makes it rotate is not only the force, because look, I can put two forces like this, apply it, and it will not translate, it will rotate. So what makes it rotate is you have to have a force. You have to have a force acting on it, and that you have to apply that force at some distance from the pivot, and we call that R. And that force has to be perpendicular to R. Otherwise, the object will not rotate. Let me give you an example for this. That door, I have to go out of the classroom door. That door. Assume that, the window. This is much easier. Look at that window. I'm going to apply force on it. And you guys tell me if it's going to rotate or not. Does it rotate? Why doesn't it rotate? Because the force has a specific direction that's preventing it from rotating. Now I'm going to do this. I'm going to push it with a force, but it with some angle. Does it rotate? Okay. Now it rotates because the force makes it a little bit rotate. It's not all the force, a component of it. Is that easier for you to push it that way, to close it, or to go here perpendicular and push it? We all have tried this. It's much easier for me to apply the force here perpendicular to that distance and push that window, then I will close it. So in order to make it rotate with the smallest amount of energy or smallest amount of force, you have to push perpendicular to that line in here. It always rotates, but you have to put more effort into rotate it if you actually push it with an angle. It's really hard. It's not that easy. But if you push it perpendicular, you push with a little force. What's important here is not only the force. That's why people, when they make those doors and windows, they put the knob at very far away from the pivot. Because what makes the object rotate is the torque. Torque. And the torque equal R times F. For simplicity for now, it's not only R times F. But for simplicity, I will say it's R times F. So in order to maximize your torque, you need to increase R. So if we put that knob in here, you're not going to have much torque. The torque is going to be small. You need to increase R, assuming that F is constant, in order to maximize your torque. That's why we put that knob far away from the pivot. So it's R times F. It's not only R times F, the angle between R and F is very important as well. It's the component perpendicular to R. So it's that force. That's important. It's the component of the force that's perpendicular to R. But if you push that way, that's not effective at all. This will not make the object rotate. So we need that component, not that component. So it's R times F times sine the angle between them. Is that true? Yes. Now, what is the angle between R and F? Now, it's 0 or 180. 0. What's sine 0? So what is the torque? 0. No torque in that case. But if you do it that way, so it's sine 90, then the torque is maximum. So it's torque equal R times F times sine theta. If you look at this, R is a vector, F is a vector. So we have to come up with some vector multiplication in here to get the torque. And that vector multiplication we did not study before. This is the time to study it. We call it cross product. R cross F. That's the torque. If you remember in the work, when we were calculating the work, we studied force dot D. We had dot product. And work in that case, that's the force, the magnitude of the force times the magnitude of the displacement times cosine the angle between them. Now the torque, it's the R times F times sine the angle between them. So simply we can actually learn now that the cross product between any two vectors is the magnitude of the vector number 1 times the magnitude of the vector number 2 times sine the angle between them. Or in other words, vector A cross vector B, that's the magnitude of A times the magnitude of B times sine the angle between them. And with this, the resultant of this cross product is a vector. While the resultant of a dot product is a scalar quantity. Torque has a direction. Torque has a direction. It can be clockwise or counterclockwise. And we use the right-hand rule to find that direction. So simply again, cross product is the magnitude of the first vector times the magnitude of the second vector times sine the angle between them. Dot product will give you always a vector quantity. So if we have a vector A equal to 3i, this is a vector, has a magnitude and direction. Vector B has 2j, That's another vector. It has a magnitude and a direction. What is A cross B? That I know that it's going to be a vector. So what will be A cross B? Direction.
Is this the same as the dot product if I times j equals 0?
No. That's a good question here. No. That's another kind of vector product. That's called, we call it cross product. So now this is the time that I should teach you how to do the cross product. But can we get it by observation first? Can I get it by observation first? Let's say that this is x, guys, this is x, this is y. So what is the direction of I? Oh, sorry, of R. It's along the x-axis. What is the direction of my force? Along the y-axis. This is x, this is y, and that's z. X, y, and that's z. So now, if I push that door in that direction, in what direction will it rotate? It's either positive or negative z. It's either positive or negative z. That tells us if you have product vector A, you cross product with that vector with B, the resultant vector has to be perpendicular to the two of them. It's always perpendicular to the two of them. X, Y, so you have Z or Z, right? So the rotation, the torque in that case is perpendicular to the R and the force.
Z cannot be that way if we change I and J.
What do you mean?
Maybe it's not it's not perpendicular to I and then perpendicular to J. It's like
Yeah, true. Yeah, I get what you mean. So if this is R and this is F, then that's going to be Z. If you do this, still vector C is perpendicular to them. If you do this, if you do this, if you do that, so it doesn't matter. It's always perpendicular to them. So the cross product of two vectors will give you another vector that's perpendicular to the two of them. How can we do this? So is it going to be K or negative K? Then, in order to know if it's K or negative K, I give you what I call the smiley face. The smiley face says I, J, K. I cross J, K. And J cross K, I. And K cross I, J. So that's the smiley face. I cross J, you get K. J cross K, you get I. K cross I, you get J. And the order is very important because if I say J cross I, negative K. And if I say K cross J, negative I. And if I say I cross K, it's a negative J. What if I say I cross I? 0. How so? Because we know that A cross B, that's A times B times sine the angle between them. Now if A and B along the I-axis, along the x-axis, the angle between them is 0, sine 0 is 0. So I cross I is 0, J cross J is 0, K cross K is 0. Now we can do any cross product.
Why don't you do it that way? Find the angle.
Because sometimes you get this. Now, what's A cross B? So you have to know.
I could get the angle, but sorry.
Yeah. So you can do it that way. It's much easier to do it that way. So in order to do that, well, what I have to say, it's A. This should give us A, which is 2I plus 3J, cross B, which is 3I minus 2K. Then 2I cross 3i, 0. 2i cross 2k. I cross k, that's negative j, so it's 2 times 2 for negative j, and do not forget that negative. I cross k. I know that k cross I, that's j, which means that I cross k, it's negative j. Okay? So you get negative j, and you have another negative in here, you get 4j. Then 3i times 3j. So 3j times 3i, cross, look times, cross. 3 times 3, that's 9. J cross I, negative k, negative k. Now, the last one. J, 3 times 2, that's negative 6. J cross k, that's I. Now you have your vector. That's the cross product of that. Okay? So now we know that the torque equal to I times alpha. Torque equal also, there are two equations to get you the torque, guys. Torque equal R cross F. R cross F. Torque equal to I times alpha. So now this is Newton's second law for rotational motion. So what makes things rotate? It's the torque. Torque equal I times alpha. What is the unit of the torque? Can anyone give me the units of the torque? Units of the torque? Newton meter. How did you know that? Torque equal R cross F. R is in meter, force is in Newton, which means the torque is equal, has the units of Newton's meters. Good. Okay, that slide tells you about that cross product. It says that if you you can get the torque in here by two ways. Torque equal to R times the theta component of F. R times that component of F. That's R times that component of F. So the torque equal R times F theta. That's one way to do it. The other way to do it, it's F times that R. This is also torque. Same torque. But the two ways give you exactly the same answer. All what we care about is the perpendicular component to that vector R. Okay, that situation will give us zero torque, and that's what we explained in here. That situation will give us maximum torque, and that's what also I have explained in here. And now Taha will solve that for us. That was one of the problems in my old exams. Most of the examples here are old exams on most of my slides. I have two rods. One, two. Two rods, two different shapes. I'm going to push each one of them with the force F. This has a length L, and that has a length L, that has a length L. Both of them are pivoted in here, so they will rotate around that pivot. Which one will have more torque? Case 1, case 2, actually they will have the same torque. Sharif? So which one will have more force? More moment of inertia. It's not with us at all. Which one will have more torque?
More torque?
Do not answer. Just look at it and have the answer. Prepare the answer. But Taha will answer it. Will answer that for us. Case 2. Good answer. Mustafa. They will have the same torque. Not that good. Vanessa. The same. ندى. Case 2. Minna. Case 2. Amira. Kurdi. Case 2. Heidi. The same. It's clear to us that we did not agree on answer yet. That means that some of us, they still have the misconception about how to calculate the torque. What is the torque? How can we calculate? It's the force times the perpendicular distance between the line of the force and the pivot. I'll say it again and think about what I'm saying, guys. Think about it, try to absorb it. Torque equals to the force times the perpendicular distance between the line of the force and the pivot. Saying that this is the force F times the perpendicular distance between the line of the force and the pivot L. So in that case, the torque equal to F times L. Right? Okay. In that case, this is the line of the force. So the same force. What is the perpendicular distance between the line of the force and the pivot? L. So actually, they have the same torque. So it doesn't matter where you apply, or how far you apply that force, the perpendicular distance between the line of the force and the pivot is the same in the two cases. Okay, guys? Vanessa? Okay, so Kordi? Okay. And that's the answer. You'll find the answer here. And we talked about the right-hand rule. We talked about the cross product. You can just go back and read them. This is more details about the cross product. We talked about, when we talk about torque, that means that it has a direction. This is a vector quantity. And we said that if the object rotates that way, this will be the direction of the torque. If the object rotates that way, this will be the direction of the torque. If the object rotates that way, this will be the direction of the torque. We use the right-hand rule to find the direction of the torque. And when I say the torque along the z-axis, then I'm talking about moment of inertia around the z-axis, and I'm talking about acceleration, angular acceleration around the z-axis. Look at this problem here. We have a nut that's stuck and we cannot solve it. We cannot actually loosen it. So a man, not that smart man, said that he will pull that with an angle, 45 degrees, try to loosen it. He put a force equal to 200 Newton, and that 200 Newton is at a distance equal to 0.5 meter from that nut. What is the magnitude of the torque in that case? Torque? So it's 100. Is it 100? It's R cross F, which means R times F times the angle between them. So it's 100. It's 100 times 0.5 times sine. Sorry, 200 times 0.5 times sine 45. That's a good answer. Then you get how much torque does that guy do? Again, if the nut suddenly turns free, now it's loose and it will rotate, what is the angular acceleration of that case? Well, if I know the torque, if I know the torque using that equation, that's what torque has used now, and we know also that the torque equal to I times alpha. If I know the torque from that equation, and if I know alpha, can I get and I know the amount of inertia, can I get alpha? So all what I need now is to find only the moment of inertia, and the amount of inertia for a rod. 1/3 ml square, and this is going to be given in the sheet. So do not worry about it. You know, all what you know is you should recognize the shape, go to the table, find out the amount of inertia for that shape. So if we know I and we know the torque, you know I and you know the torque, you can simply go and calculate alpha. I'm giving this example for you guys because torque can be found using two ways. And sometimes I do not give you the torque at all. I give you R and F and I give you I until I ask you to find alpha, and B will get stuck. You should realize that the torque has two ways to be calculated, and in that case you have 5 unknowns. If you know 3 of those unknowns, you can get the other 2, which is the torque and whatever other unknown is. How many of us went to his mechanic to fix any part of his car? No one has car? No one? How many of you tried to fix a part of his bike? No one has bike? Sometimes when you have a nut that's really actually tightened and you want to loosen it, what you do, or you have watched that with some mechanics, they put the wrench in there and they stood on it, right? And sometimes, so they can put lots of force in there. They are increasing the force to do that. And sometimes they put another tube, metal tube in that wrench, and they stand on it. And they do that to increase the arm. Because what makes that thing rotate is not how much force you put in it. It's the torque. So, and you can increase the torque if you put the maximum force and you cannot loosen it. Other way to loosen it is to increase the R. You increase R. So this is a practical application for torque. We see it in everyday life. We go to mechanics and we find that mechanics, they do that all the time without knowing why. Now we know why. Work. If I'm rotating something, if I rotate this, do I do work? 2 minutes. 2 minutes. I know that I can beyond my time. Can I do I do work to do it, to rotate it? Yes. How much work do we do? Well, if it's a translational motion, you're right. If it's a translational motion, it's force times distance. Sorry, dot displacement. Yeah. But if you rotate it, what's the equivalent to force in rotational motion? Torque. What's the equivalent to displacement in rotational motion? Theta. So Ali actually gets us Ali's law, which is that whole proof, work done in rotational motion equal to T, tau, torque times theta. That's the work. Is that a dot? Just simple multiplication. So guys, I'll stop in here and we'll continue this after the Eid. Have a nice Eid. Do not eat much